Hi, Cliff. I just wanted to record how I'm checking the quality of the calculations at the Jet Propulsion Lab's Horizon system. This is an ephemeris, and in this case, what I'm doing is I took a geocentric position for a target body at this location, which happens to be a particular Vanuatu Island earthquake that occurred. And I just arbitrarily first set it at 0, like here. I set it at 0 meters relative to WGS 84. Is that the way to say it? WGS 84. Anyway, then I did it again at so at 0 meters and 1 meter, and then what I did, I'll show you in 1 second. So, and I did this for every 2 seconds. They won't let me go over like 50,000 rows, I think. So I just got as many as I could grab. Now the output from this is the vectors x, y, and z, and then the velocities, the light time, the range, and the range rate. That's what they're showing here. This is intended for tracking objects, but I made the object the station in this case. So, and okay, so these are the 1 meter. 1 meter, and let's see. Okay, and these are the 0 meter calculations. Let me stick that there. Okay, so I'm taking the difference between those two. So this and this is the calculation. It's a little elliptical, but it's the square root of the sum of the squares, x, y minus y, z minus z squared. And then I subtracted 1 meter, which is the nominal distance involved. I converted these numbers in kilometers by multiplying by 1,000, and then I took the residual, the difference between them, and multiplied by 10 to the 9th to get them into nanometers. So this is the difference between the two calculations in nanometers. And then for counting purposes, just so I can see that, first of all, the mean and standard deviation, even with different samples, I still get a mean difference here. So could that mean that there is I'm not quite sure why that is, but it's consistent that they're high by 0.295 something or other nanometers. And I'll look into seeing why that's off. And the standard deviation is consistent. I truncated them so that I could count them, and I did a standard crosstab in here and counted the truncated distances, and you can see they go up to roughly plus or minus 15 nanometers, and then they're normally distributed in here, which is what I was looking for. The error should be because of rounding and, basically the whole apparatus of their calculations. I'm just checking to see if it's consistent in there. So that's just a check that, I want to know what the quality of their calculations is. This is the way I check somebody else's calculator. I can run samples run a few, if I could, I'd run 1 million samples, and then, look at the results of what they give me back. Now I'm going to do the same thing for like 1,000 meters and for specific things. This is my current reference that I'm going to use. I'm going to run the station this way at 0 meters, or at the station, coordinates from the center of the Earth, and then I'm going to do it again for the earthquake coordinates, and this is rotating, and I don't know how they're rotating exactly. I think I have an idea, but I'm going to have to I'm going to see if I can reproduce this table myself. It's probably easier to reverse engineer the table than to go through and try to find their calculations. It's unfortunate, but that's the way they are. So this is 3,200 seconds. Okay. Let's save that. All right, so I just wanted to show you there. I'm really looking for some comments and suggestions, so I hope you can tell me a better way to do this. I always just brute force it, kind of. I just check, find a calculator. I'm trying to tie. This is the Jet Propulsion Lab Horizon system, and I'm trying to tie that. Let me move. Let's see. I saved that. Let me move this out of the way. I'm trying to tie the Horizon system right now to this system. Okay, so here's there's a whole database, of earthquakes, and I just picked a current one. So here, and these are stations. The triangles are various reporting stations, and what do they say? They have move down a little bit. They stopped it at 5,000. Okay, here's a close one. This is the Australian Charter Towers seismometer, and that's actually a very good one. That I used that. I calibrated that when I was doing the gravity calibrations for the network back in 2013. So that is the all of the Australian seismometers are good ones from my point of view. They can all be used as gravimeters, and that whole business that I told you about was I calibrated them to use against the sun and the moon, so I could use them as gravimeters, absolute gravimeters, in the sense of reporting absolute units tied or checked against the sun and the moon in a consistent way. I'm not too concerned right now for accuracy as more stability. If I can get basically I can get every one of these stations reporting every one of them blocked to a certain through a fixed process to the sun and the moon, and through a fixed process to the Horizon system, therefore to the JPL ephemeris, and then I have a way to trace everything through. I may not get it right, but at least I know how they're connected, and I can gradually weed out and improve. Just this is linking models 101. All right. The problem I have in here, I couldn't find a way to copy this information out. You cannot. I'm trying to drag and drop. You cannot highlight this table and copy it, and you can't. As far as I've tried looking all over here, I don't find any way to download it. There's no download button, so I can't get this table. these are the reporting stations that they, that had data on this thing, and I'm preparing to run all of these to see what the geometric distance is from the let's see if I can get that off there, from the geometric distance from the earthquake here to each of these stations. And the seismic wave is going in a curve following the Earth. The gravity signal is ahead of it, moving at the speed of light / gravity. The speed of gravity, I'll just say it that way. Moving at the speed of gravity, speed of light, from here to there in more or less a straight line. I know down at the deep levels that gravity doesn't travel exactly in a straight line. These waves don't, but for all practical purposes, they should be straight rays, and that's something that can be checked eventually if we get better instruments. But right now, what I want to do is I want to say, well, okay, let's zoom out here. Oops, wrong way. Zoom. Okay, from the whole Earth, these other guys are on the opposite side of the Earth. They see the gravity signal. It should go straight through the center of the Earth without interruption. For a big earthquake, we can measure that now using our existing seismometers, calibrated as gravimeters, and I'm trying to squeeze out as much as possible. That's what I'm going through right now. I think I can use the fact that these occur at a certain time. I know some things. Let's see, what is the, hang on, I'm going over here to my spreadsheet. Okay. The average radius, 6371 meters, divided by 2/200ths of a second, okay, is the time it takes to go from one diameter times twice the radius. Okay, so this is pretty slow in a way. So the gravity signal from the opposite side of the Earth is taking 4/100ths of a second about. And if I'm sampling at 40 samples a second, I'm actually moving 2 pixels roughly. Okay, my time pixels, my sample times are such that I can actually resolve the difference between these two. So I can say, okay, let me move this one sample over and see it. Now, if I can get let me do that again. I'm just going to use 0.04 seconds to cross the Earth. So if I use something from there, if I could sample at, say, 40 kilohertz, like I put or make it 20 kilohertz, which is an easy audio signal A to D converter, that I stick it on the seismometer instead of what they got, and then do it. So let's do that at 20 kilohertz, 20,000 samples a second. So times 20, 800. So I could check, do I shift this there? And I can actually come in and measure the speed of gravity from there, or I could be that precise. I can be down to very particular. I'm actually going to get down to which specific pixel, which specific sample at the time is there. So if it's on the opposite side of the Earth, they're gonna, if I measure it locally, they won't. You don't have to make any adjustments. But if I measure it at a large distance across the across the Earth, then it'll shift. If I was doing 20 kilohertz, then there. Now I've been trying, asking people to try to get up to the gigahertz. We do have gigahertz A to D converters, and if I take that 0.044 seconds across the Earth and multiply it times 1 gigahertz, gigasamples per second, and that's 40 million pixels, time pixels, that I can use to distinguish when things occur. So you can actually get down to exactly how far away something is. Now, are there some issues here? Yeah. First of all, you're going to have to put an amplifier on your signal to just punch it way out there, and there's going to be a heck of a lot of noise in there. But the correlations between this side of the Earth, like a station here and a station there and a station there, are going to be very precise. If you're doing it this gigahertz frequencies, you're gonna be able to just setting. It's like trivial to set the. You calculate the geometric distance. You work out the delay in samples that you need to shift the signal, and then you start looking around. It's not going to be exact at first, but I can go in and say, well, okay, they're 0.05243, 48 seconds apart. These two, I got two stations, from the earthquake to the station, it's this far away. So I take the geometric distance in meters, divide by the speed of gravity, speed of light, and I get this number. I multiply it by my sample rate times, say, 1 megahertz, and I have to shift by 5248 samples to do the correlation, or at least to start looking. So that's my strategy in here, how to go in and use that. Unfortunately, I don't have anybody who will listen to me yet. That we need, let's sample the doggone things there. Even okay, let's do that. Let's do 0.05452. Okay, so let's say that's our distance in seconds that we have, and we're using 20 kilohertz. We just put an audio sound card onto our seismometer. We don't do it really cheap. Doesn't have to be very precise, because we're going to walk it in, multiply this times 48,000 is standard, 48,000 samples a second. 12-bit, there's a lot of 12-bit, some 20-bit audio things. Anyway, and we have to shift 260 samples for that particular one. So, if we measure this in sample distances, then we're like some of these guys. They're like the same. They're almost in the same sample, but it doesn't take long. And if you divide the Earth up into it's what is it? The whole Earth is 0.04 seconds across, and I multiply that by 48,000 samples per second. So the Earth is about 1920, about roughly 2,000 samples, audio samples across. So a standard audio sound card can divide the Earth up into this many samples. Even at our current level, we can start imaging things somewhat. And I'm trying to get an image of the whole Earth, at least the common earthquakes around. Can all of these? Let me not get into that. Yet. So that's my rough strategy here. These are my baby steps that I'm taking to get this worked out, something workable.